Hi guys, so today we're going to be doing sketching sine and cos graphs. So this is a little bit of a long one and a little bit of a hard one, so a little bit tedious, especially when we have to find x-intercepts and endpoints. So this is from 2.5 of the jacplus textbook, and these are the worked examples. So let's get started on this sine graph here. And before I draw this, I'm just going to point out the normal sine graph, or the parent graph for sine. So if we were doing a table of transformations, our x and y, and this would be our parent graph. So there'd be the amplitude of 1, so from 1 to -1 there, and then you'd have a period of 2 pi. And cos and sine have a period of 2 pi, and that's because from the unit circle, your value will repeat after 2 pi. So like when we do general solution, we always add 2 pi for cos and sine. Tan's a bit different, and we'll deal with that later. So notice how we've now got to look at our period and amplitude of the actual graph. So our amplitude here is 3. So what that does, it'll mean that the height and the highest and lowest values of our graph are 3 and -3 respectively. So, and then, well, the period is determined by this part here. So the period is going to be 2 pi divided by whatever's in front of the x, and in this case it's 2, so 2 pi divided by 2 is pi. So what that means is that this 2 pi is going to change into pi. So now I've gone from the graph of y equals sine x, and I probably should have pointed out that that was where we had 1 and -1 and 2 pi here, so that would have been y equals sine x. And then, well, when we change these and put the amplitude of 3 and we apply the period of 2 pi divided by 2 is pi, so there we go. That means that we're now saying that is 3 sine 2x. So that's almost the whole equation. So we've essentially, the period and amplitude are dilations to the graph. So although I haven't changed the original graph, obviously it's stretched up from 1. So if it was the original graph, it would have just been, up to 1 and down to -1, and it would have been going to 2 pi. So now we've squashed it in ways, and we've also stretched it this way. So there is 3 sine 2x, and we don't need to show the squash and the stretch there, as long as we know what the period and amplitude are doing. Now the final bit is this plus 4. So I'm going to do that, and so now if I add 4, I'm going to be going up by 4 units. So I'm just going to draw that separately. So if I go up by 4 units, everything has to add 4. So here I add 4. This is 0, I'm going to be adding 4, and this I'm going to be adding 4. So I'm adding everything to my y, 4 to every one of my y values. So the 0 becomes 4, the 3 plus 4 is 7, and then -3 plus 4 is 1. So now it's going to look like this, and this is just one cycle up to pi. So this is from 0 to pi, and if we look at our domain here, it's actually 0 to 2 pi. So now I can say, well, I'll put the next one, look, I'm going to do it in a different color, just so you can see how it's just repeated there. So this is going to go to 2 pi. And then for this one, we don't have any x-intercepts, which is quite nice. We can see that this is going to be 2 pi 4. We can see this is going to be 0, 4 here. So they're my endpoints, really easy to put on. And then look, I can add the turning points very easily, so I will do that. As we know that this is pi here, so if that's pi, then, well, halfway would be pi on 2. And this would mean that here would be pi on 4, 7. So of course, the top value is 7 there. And then down here to this minimum value here, so it's 1 pi on 4, 2 pi on 4, and then will come 3 pi on 4. So here would be 3 pi on 4, 1, 4 pi on 4, which is here, 5 pi on 4, 6 pi on 4, 7 pi on 4, and of course 8 pi on 4, which is our 2 pi 4 that we've written in there already. So that would be that. That would be no x-intercepts. That's really good, and we can easily put the turning points in. Often you are not expected to do the turning points, but for one like this, no doubt they would want you to show it, because it's really easy to just count them in there. You don't have to do any sort of algebra work. Let's move on. So I think we've finished that one. The next one is a little bit more tricky, and this is where we have to find a equation for this function here. So this is a cos graph, and they've told us this. It's a cos graph because, I mean, it could be part of a sine graph, but you know, they're telling us it's a cos graph, and they say we want the mean, the amplitude, and period. So let's have a look. The top value, so the maximum, equals 4. The minimum equals -8. So then, well, if we wanted to find the mean value, or mean position they're calling it here, well, we're going to have 4 plus -8 divided by 2. So the mean is the average. So we take the top and the bottom and we divide it by 2, and we get -4 on 2. Which is of course -2. So that means that our middle line there, if we were going to draw a middle line, would be -2. And what this means for the graph, it's been moved down by 2 units from an original cos graph. Other things have been done too, but it's moved down by 2. Let's look at the amplitude. And really the amplitude we can get just from the picture here. We know this is a 4. And we know this is a -8 here. So you can see that from the mean position, we're going up by 6 and down by 6 to get to the maximum and minimum respectively. So the amplitude is 6. But if you didn't know that, you could have said, well, 4 minus -8. So you could have subtracted, divided by 2, and that will give you 6 as well. So the amplitude is 6. So we've got amplitude, we've got mean position. Now we just need the period of the function. So, well, there's 2 ways you could go about this. You could say, well, here is the middle of the cos wave. So that would mean that over to here would be 2 pi on 3. So 2 pi on 3 would be there, and that would be our period. And or you could count, 0 pi on 6, 2 pi on 6, 3 pi on 6, 4 pi on 6, if you wanted to do it like that as well. But I think it's actually a lot easier just to find the that you've got the middle of the cos wave there. So that means our period, which is how far it goes on the x-axis to have one cycle of the graph. In this case, it's a cos graph. In the previous one, it was a sine, and that's 2 pi on 3. So we've done the mean, we've done the amplitude, we've done the period. So now we need a possible equation. And look, I'm going to say y equals a. A is, usually the value you use for your dilation, cos of nx, and then plus, we usually use k here, but I mean, you could use b or c, whatever you like, whatever pronumerals you want. They don't give us an equation to start with. So let's see, what have we already got? We know that, well, we have a 6 for the amplitude, and we also know that this cos graph is upside down. So our positive cos graph is like that, the smiley face, and the negative cos graph is like that, like parabolas. So quite easy to remember. So this is -6. -6 is the amplitude, or 6 is the amplitude, and we've got a reflection, so it's negative. Then we've got, well, cos, and now the n value, you must be careful because it's not 2 pi x on 3. That's wrong. So remember, the period is 2 pi divided by whatever's in front of x. And, well, we're going to call that n, because we've called it n here. So, and we know that that's 2 pi on 3. So now, you don't have to do any sort of cross multiplying or anything. You can see that because your numerators are the same, and you've got an equal sign, you can essentially cross them out and say n equals 3. So now we can say 3x, and then, well, this plus k thing, and we know that the plus k refers to our vertical shift. So the vertical shift we already know, because, well, we saw that our mean value was -2. So that means that our normal cost graph, which the mean value would be 0, it's gone down 2 units. So in other words, our k value is -2. So the equation here would be y equals -6 cos 3x minus 2. So that would be that. All right, let's move forward. Right there. Okay, so now we get to one that's a little bit more intense, and we need to find x-intercepts for this one, no doubt. So let's see. Let's see how it goes. So look, I'm going to just start by saying the normal cost graph. So my normal parent cost graph would be this, and it would be 1, -1, oops, not -2. And then the period of cos is 2 pi. So this would be y equals cos x, a normal cos x. And what we can see is that a number of things have been done to the graph there. We've got a 4 here. So, well, straight away I can see that is going to turn my, that's my amplitude. It's going to turn these values of 1 and -1. I'm going to make them into 4 and -4. So that means now my parent graph turns into y equals 4 cos x. So that's easy enough. That's a dilation there. Let's see another dilation. We've got this 2 here. So that's to do with the period of the function. So it's going to be period equals 2 pi, because cos repeats in the unit circle after 2 pi. So 2 pi divided by whatever's in front of the x, which is a 2, and that means that our period is going to be pi. So that now will alter this. So I might do it a different colour. That means that now this is just going to change into pi. And I should highlight that so you can see what value gives what, and these ones in yellow. So now my equation is 4 cos 2x. So we're getting there. We've now just got this pi on 3, and you can see that I'm ignoring the domain for the meantime. So I'm just dealing with one cycle of the graph from 0 up to, well, pi in this case, because the period is pi. So now I want to look at what this pi on 3 does. And, well, this is where it's a little bit tricky, because we're not moving by pi on 3 in the negative direction of the x-axis. We're actually moving by pi on 6. So I'm just going to write this out again. F of x equals 4 cos. There's a 2 in front of the x. You need to take that out. So this is really, really important, and a lot of people will forget to do this. So here I've removed the 2 from everything. If you don't do that, then, well, you're going to get it wrong, because you're going to have a pi on 3 movement in the negative direction. So that's really important, and it's the same idea like if we have a hyperbola where it's 2x plus 4. Your asymptote is not at -4, it's y equals 1 over 2 x minus 2. So when you draw that hyperbola, you would have at, we wouldn't change the positive to a negative, of course. So then you'd have your asymptote at -2, not -4. So it's important that you remember hyperbolus, truncus, root graph, cos sine, everything you have to remove when it's connected to the x. So now let's see what that does. And I'm actually going to redraw this so we can see clearly what's going on there. So now what happens is that I've still got the same shape. I've still got a period of pi, but now on everything, I'm going to be minusing pi on 6. So that would be minus pi on 6 and 0 minus pi on 6. So every x value is going to be minus pi on 6. So I'm not going to worry about the intercepts yet. That will come afterwards. And but I'm going to do that. I'm going to draw the general shape there. So I've got pi on 6 to negative pi on 6, because 0 minus pi on 6 is negative pi on 6. And then pi is 6 pi on 6. So that means we're going to be going to 5 pi on 6. So I still have at 4 and negative 4. There's my, my maximum and minimum lines. And well, we have not moved up or down anywhere, so don't have to worry about the, vertical, any sort of vertical movement. And now it's going to be something like this. And this is one cycle so far, and I can see that it's going to be a positive y-intercept there. I can see that because, well, it's got to be, it's symmetrical, so about the midpoint there. So you've only got pi on 6 on the side of the y, on the left side of the y-axis, and you've got 5 pi on 6 on the other side. So it's clear that it's going to look like that. But when you find your y-intercept, that will sort itself out anyway. So let's see. We've considered the period, we've considered the amplitude, and we've considered the horizontal shift. So now let's go about finding the x-intercepts and applying the domain. So I might worry about the domain now. So the domain is from, I better double check that, 0 to 3 pi on 2. So I can see clearly that I'm going to be cutting off that bit there. That's easy. What's not so easy is adding on a bit more. So what I'm going to do, I'm going to add on a whole nother cycle and then choose how much of it I need to cut off. So 5 pi on 6, if I want to go another cycle, remembering that in the cycle is pi and the period is pi, so I'm going to be saying 5 pi on 6 plus 6 pi on 6. So it's going to be 11 pi on 6. So if I then draw another wave, it's going to be like this. And well, I'm not wanting to go to 11 pi on 6. I want to go to 3 pi on 2. So let's see 3 pi on 2 with a denominator of 6. So times 3, that's going to be 9 pi on 6. So I'm guessing that I'm probably going to go to somewhere here. And at the moment, I'm not sure, it could be that it goes up to there. So in other words, the second part of my graph, I definitely know I have this. I definitely can see I'm going past the turning point because it's more than half of the next cycle there. So if you think 5 pi on 6 up to 11 pi on 6, you've got 6 pi on 6 in between. There to there, there's 6 pi on 6. So 5, 6, 7, 8, 9, that's 4 of them. So 4 out of 6, you've got 4/6 of this wave you've got to include. So it might look like that, or it could be that it continues up to there, and we'll find out. But I don't, it's definitely not going to go there, so I'll rub that off. So I've cut off that top bit for sure, and maybe even the part from those in between those two endpoints that I've guessed there. So let's see. I think I've got 1, 2, 3, or maybe 4 x-intercepts, but definitely at least 3. So let's go. Let's find the y-intercept. That's when x equals 0. So our equation 4, so y equals 4 cos 2x plus pi on 3. Oops. So you can do it as 2 open brackets x plus pi on 6 closed brackets if you prefer. It really doesn't matter. And we're subbing as 0, so I'll just do that. So that means I'm going to get y equals 4 cos pi on 3. Now this is where you need to use the table of exact values, and like BODMAS, we know that more important than multiplication is cos or sine. So cos of pi on 3, we look, here is pi on 3, here is cos, where they meet, it's half. So that equals half. So we've got y equals 4 times half. And notice that in cos of pi on 3 is in quadrant 1. So that's why we've got a positive, positive half there, not negative half. So, and you can see anyway that your y-intercept is going to be on positive 2. So that's 0, 2. Let's go, so we've got y-intercept, and now we're going to do maybe the other endpoint. I'll do that next. So the other endpoint, so we go from 0 up to 3 pi on 2. So end point, which is the right endpoint. So notice that the left endpoint was the y-intercept. I might write that left endpoint. So that's not always the case. You know, if your left endpoint is from negative pi, like if your restriction is negative pi to pi, then the left endpoint would be negative pi. The right would be positive pi. So let's do the right endpoint, and that's going to be when x equals, now I forgot again, 3 pi on 2. Okay, so let's have a look. I'm going to draw it. And we've got, well, 3 pi on 2. So we've got y equals 4 cos 2, 3 pi on 2, plus pi on 3. And let's see, y equals 4 times cos 2 times 3 pi on 2. That will cancel. So that's just 3 pi plus pi on 3. So this is the part where people get a little bit unstuck. So 4 times cos, and this is going to be, well, let's do common denominator. That's 9 pi plus pi is 10 pi on 3. And now what we need to do, we have to count around the circle. So I'm going to draw pi on 3. And I know that the cos of pi on 3 is half. So remembering cos is your base of the triangle there. And now, well, if we count in 3s, so there's 3 pi on 3, 6 pi on 3. So let's go 0, 3 pi on 3, 6 pi on 3, 9 pi on 3, and then we need a little bit more for 10 pi on 3. So we see that now it's going to be in this quadrant. So we're putting the triangle in this quadrant. It still has a pi on 3 angle here, but we can see that the x value for this point is going to be negative. So that means that this is negative half. And that's 4 times negative half, which is negative 2. So that means our endpoint is at 3 pi on 2, comma neg 2. And I'm going to add that straight in. And that tells me, which is quite nice, that I don't have that part there. So I'm cutting off all that, and my endpoint is here. So I'll just delete that because we haven't got so much room. And 3 pi on 2, comma neg 2. So that's that point there. So we've got the two endpoints. And now really we just need the x-intercepts. We'll do those now. So I can see I've got 3 x-intercepts. And look, with 3 x-intercepts, I would probably go around the unit circle. If I had 5 x-intercepts, even 4 x-intercepts, I would probably go for a general solution. So you want to choose what's the most appropriate method. So now we've got x-intercepts, so I'll do that. So x-intercepts, y equals 0. And this is going to be, well, where's our equation? 4 cos 2x plus pi on 3. So 4 cos 2x plus pi on 3 equals 0. So we're subbing 0 for y. This is one of those things. Let's divide by 4. Cos 2x plus pi on 3 equals 0. And this is one of these where we want to let z equal 2x plus pi on 3. So just like we did when we did the solving. So therefore cos z equals 0. And now we can draw it and solve. So, well, when cos is 0, people are going to put it here. But of course it's not there because, well, that's when you're measuring your angle, you measure from 0, but don't be fooled. Cos is not 0 there, cos is 1. The x value is cos. Cos is 0 here, cos is 0 here. So we can say going to here is pi on 2. Z equals pi on 2. 1 pi on 2, 2 pi on 2, 3 pi on 2. So that will be 3 pi on 2, Z equals 3 pi on 2. And look, I reckon, we've got 3, so I'll go around to the third one as well. And I'm going to go 1 pi on 2, 2 pi on 2, 3 pi on 2, 4 pi on 2, 5 pi on 2. So Z equals 5 pi on 2. So let's see what we get there. Z is 2x plus pi on 3. And look, I might just change this to a 6, and this will be 2 pi on 6, and that would mean this is 3 pi on 6, because then I've got a common denominator, 2 pi on 6. So it's just common denominator there, and that's going to equal 3 pi on 6, which means, 2x equals 3 minus 2 is 1, so that's pi on 6, and x equals pi on 12. So that's definitely within the domain, pi on 12. Let's put it in on the graph straight away. That must be here. And always put coordinates. They'll never say don't do coordinates, but they may say do coordinates, and if you just do a little dash, then, well, you lose marks for that. So there's the first one. Let's go the next one, 3 pi on 2. So that means 2x plus 2 pi on 6 equals 3 pi on 6. 2 times 3 is 6, 3 times 3 is 9. So 9 minus 2 is 7. X equals 7 pi on 12. So that means that fits into the domain, 7 pi on 12. So 7 pi on 12, 0. And then finally, we've got one more, so I'll do that. So Z 2x plus 2 pi on 6 equals 6 times 3, 15 pi on 6. So 2x equals 15 minus 2 is 13 pi on 6. And x equals 13 pi on 12. And I believe that the domain was to 3 pi on 2. So 3 pi on 2, 2 times 6, 3 times 6 is 18 pi on 12. So this is still within the domain 13 pi on 12, and we can pop that straight in. And look, there we have it. It's a little bit messy, but you can see all the key features there. So we have the y-intercept, the x-intercepts, and the endpoints shown, and the shape. We don't need to do the turning points for this, and in fact we will not do the turning points for this. They will most likely state, that you wouldn't have to do them for that one. That is the end of our 2 graphs. I will do the third example in a separate video.